So Learning Unit 4 is probably going to be one of the most challenging learning units that we're going to work through. This, and then when we introduce equilibrium in our next learning unit. So these videos are intended to make sure we do the best to kind of prepare ourselves to be successful as we work through problems in the class. So they are probably going to be a little bit on the longer side, so I'm going to apologize ahead of time for that. But again, I hope it serves the purpose of getting you well prepared to think about doing problems in class. So 4 skills that we're going to have over 4 lecture periods to introduce this concept of kinetics. So the first skill that we talk about is reaction rates and rate expressions. So this is the first time we've kind of talked about how fast reactions are. So even when we talked about that example of putting the Diet Coke versus the regular Coke in the freezer, and we asked the question, which one would freeze? And I even think I asked it, which one would freeze first? But that's not necessarily to imply that both of them would necessarily freeze, right? Because if we're above a certain temperature, the regular Coke one would never freeze. So this is really introducing a new concept that we are really thinking about how fast something happens. So when we think about how fast, we need to think about a chemical term, and it's not just specific to chemistry, but it's called rate. So rate is just a change in some variable per unit time. So we often think of rate or speed in terms of rate of motion. So when we think about, for example, a runner, we might think about their speed in terms of meters per second. For cars, it might be miles per hour. But what we can see there, and in both cases, we're measuring a change in position, the number of meters that a runner has traveled or a number of miles that a car has traveled per change in unit time, per second for the runner or per hour for the car. So that concept of thinking about rate is not going to change when we talk about rates of chemical reactions. But now the numerator is going to be different. It's still going to be per unit time, but now what we're changing is the concentration of reactants or products, as we'll see, per unit time. So let's take a very simple reaction, and as we go through these first videos here, we're going to be using pretty generic reactions. So as A is converted to B, we can define the rate of this reaction as the change in concentration, as we'll see, of either A or B, as a function of change in time. So as a function of A, remember we always think about final minus initial. So when we have this concentration at time 2, that's really representing our final or our later time. So one thing that's important is when we're talking about reactants, we're going to see rate with a negative sign here. That means that we are decreasing concentration. Concentration is changing. Okay, so the rate is really going to be a minus the change in the concentration of A as a function of a change in time. As a function of B, now because B is a product, it's appearing, by formalism, we put a positive there. So sometimes we're adding positives or negatives to things because we know what's happening, right? Rate is always going to be a positive process. So let's see if this makes sense here, right? If we're talking about the disappearance of a reactant, that means the concentration at time 2 is going to be a smaller number than we started out with. So smaller number minus larger number is going to be negative. That's why we need this negative here. So at the end, we end up with a positive value for reaction rate. Reaction rate is always positive. As a function of a product that's appearing, now the product that we have at time 2, that later time, is going to be a larger number. So final minus initial gives us something that's positive. So we don't need to write that positive there, but just as a way to kind of contrast what we have here, we basically are going to have a positive value there for this, so that reaction rate ends up being positive. So one of the first skills we need to know how to do is do what's called write a rate expression. So writing the rate expression has to do with using coefficients that's in a balanced chemical equation and writing something in terms of either disappearance of reactants or appearance of products. So let's see if this makes sense here with a generic reaction. In this case, we're saying A plus B goes to C plus D, and we've got the corresponding coefficients in front of this balanced hypothetical equation here. This is how we write a rate expression. Now, it's really important as we go through all of these different pieces that we understand what a question is asking. So to write a rate expression, we basically are going to take the change in the concentration of a species as a function of a change in time. So it's delta concentration of that species over delta T, delta time. Because A and B are reactants, that's why we put these negatives in here, okay? And then coefficients become fractions. So if this was a 2A here, this would be a 1/2 here. We're going to do an example in a minute to sort of practice, but this is how we would write a rate expression. We can express the rate of this generic reaction in terms of the disappearance of either of the reactants or the appearance of either of the products. And these are going to be important because it's going to allow us to kind of relate these two species together. So again, this is just in words what I said here, writing a rate expression. Okay, we can write it like we have here. Using a rate expression is what I was just indicating on the previous slide. We can kind of put some pieces in. So we're going to go through an example here in just a second. But if we're going to use a rate expression, what we want to do is treat the rate expression like it's an algebra problem. How many times do we say that so much of chemistry kind of comes down to solving an algebra problem? This is how this is going to work. What we're going to do is the two parts of the rate equation that have some information that's provided, we're going to set them equal to one another because the rate of the reaction, look at these are all equal to one another. So let's say we knew the rate that D was appearing at. That can allow us to relate it to the rate that A is disappearing. Okay? So again, we're going to set those two parts of the rate equation or the rate expression equal to one another. And when we talk about the parts, okay, this is what I'm referring to as a part. So this whole thing is going to be equal to this whole thing. Now, maybe they give us some information here. For a rate that's given, we're going to replace only this part. So let's say that they gave us the actual rate that D was appearing. We'd put that numerical value in here, but we'd keep this fraction in the beginning. Okay, for the rate that's unknown, again, we're only going to replace this part with our variable, which would be like an x, and then we keep the fraction. I'm going to go through an example here so that we can practice this. Solve for x, and again, that's going to be our answer. So let's run through a simple problem here to think about this. Here's a real reaction, right? We've got two hydrogen gas combining with oxygen gas to give us water. This says express the rate in terms of changes of hydrogen, oxygen, and water with respect to time. This is asking us to write a rate expression. So let's talk about how we go and make a rate expression. You say rate is equal to anything that's a reactant is disappearing. Okay, our coefficients become fractions. So let's take this for the hydrogen. Okay, that 2 becomes 1/2. And then it's the change in the concentration of H2 as a function of change in time. Because there's 3 things in this equation, I have to write 3 pieces here for my full rate expression. I also have another reactant that's disappearing. The coefficient is 1 in front of this, so I don't actually need to write this. Okay, but it is a minus that's there because it's a reactant that's disappearing. And that's equal to the appearance, and again, I've got a coefficient there, so that becomes 1 over that coefficient, so 1/2, okay? And then it's a change in the concentration of water as a function of a change in time. So hopefully that made sense with how you write a rate expression. Now let's practice using a rate expression. So now they're telling us that when O2 is decreasing at 0.23 moles per liter per second, so that's molarity per second, okay? That's telling us that we're having this value be equal to that. We want to know what is the rate of H2O that's increasing. So let's follow the steps that we practiced there. We said we're going to take whatever those 2 pieces are, and we're going to set them equal to one another. So this guy, and we're going to set it equal to the one that has to do with water. So that's, again, a positive delta H2O is a function of a change in time. Now, what I'm going to do is I am going to substitute this piece in for the 0.23. Okay, oops, wrong one there. Hang on. This guy, put it in for the oxygen here because that's what that is. But O2 is decreasing. So this guy comes in for here. Okay. Now, if there was a fraction in front of that, I would still keep the fraction, but there's not. So again, I'm going to have 0.23 moles per liter times second. And this guy is going to be my x. But remember, I only replace that part of it. I have to keep that fraction in front, equals 1/2 x. Now this is pretty straightforward. 0.23 equals 1/2 x. So when I go and I solve this, x, which is going to be the rate of appearance of water, is going to be 0.46 moles per liter times second. So it's molarity per second, concentration per second. Now if we think about this, this should make sense, right? We're going to be making twice as much water as we use up oxygen. That's just what the stoichiometry tells us there. So it should make sense that the rate of appearance of water should be twice as much as the disappearance of oxygen. Okay, so that's writing a rate expression and then using a rate expression. The next thing that we're going to talk about here is how we can look at and use experimental data. Now, we're not going to do this a lot in lecture just because it's time consuming and so forth. We'll have time to think about it in lab, but I do want you to understand how this data is acquired. So we can graph data. Data for graphing here is always going to show concentration, that's our y variable, as a function of time, our x variable. So again, we can see here we've got a product that's appearing or reactant that's disappearing. So this is showing this data graphically. What we're going to talk about is 3 different ways that we can think about kind of this rate data from this experimental information here. We can define rate as the slope of a curve. Look at what the slope is. Slope is always a change in y over change in x, right? That's what slope is. A change in y, that's our concentration, over change in x. That's how we defined chemical rate. Change in y, change in concentration, over change in x, change in time. So if we get the slope of the line at any point here, what we're going to get is the rate of anything from this line is going to be the rate of a product that's appearing. Anything on this line, a rate of a reactant that's disappearing. Okay, so highlighting, we need to determine a change in y and we need to determine a change in x. Okay, and that's going to give us our rate by looking at those 2 pieces of information. So now I'm going to show you from some actual data how we get 3 different kinds of rates. And I do want you to know the difference between these rates, and I want you to be able to know the important one that we're going to use as we move into skill number 2. Okay, average rate. So average rate is the slope of the line joining any 2 points. Okay, there can be many average rates depending on what time span we choose. Let's imagine this from a race, like a runner in a race, for example, right? When they start out of the gate, they might have the fastest rate possible. So if we looked at, for example, their rate of speed over the first 10 seconds of the race, that's probably going to look different than the last 10 seconds of the race than it would if we took their average over the entire race. Okay, so it depends on which time span or time frame we look at. This is pretty easy to kind of figure out from graphical data. You basically need to identify 2 points on your graph. Let's say we picked the first point here and the last point here. Those are going to have x, y coordinates that we can then use in our calculation. So if we use the difference of the y coordinates, that'll give us delta y. Difference in the x coordinates will give us delta t. Take the difference, I should say the ratio of both of those, delta y over delta x, that will give us the rate. So again, we can have different average rates depending on the time frame that we're looking at. And I hope my runner analogy kind of made sense. Depending on the first 10 seconds, the last 10 seconds, or the entirety of the race will give us different average rates. Same is true with chemical reactions. Now, an instantaneous rate literally just means, hey, I'm taking a picture, a snapshot of a runner in a race, and I'd like to know what was their speed at that given time. This is a little bit different because what we're going to do is we're going to just choose one single point on our line, and then we're going to try to make a tangent to that line to give us our x and our y coordinates. So it's almost like we're making our x and y coordinates from this tangent line. So we're estimating using a tangent that we're drawing. So just by doing that, it's hopefully obvious that we're introducing some error in this process. So this again is a snapshot in time. So imagine, if you will, if I've got a line, the middle of my pencil here is a line on my curve, and as I'm following along the curve, you can see that the angle of my pencil is changing. right? That means my rate is changing. So it gives me kind of a snapshot at any given point in time with what my instantaneous rate is, okay? Now, a special kind of instantaneous rate is what we call the initial rate. So again, if I'm looking at my pencil here, my pencil is sort of traveling along the curve of this line. So imagine this line that's right here. And imagine that I'm going to take my pencil and I'm going to hold it on a tangent to that line. You can see that as I follow and trace that line, the slope of my pencil changes. The slope is fastest. I'm fastest when my reaction has just started. Okay, same with a runner kind of starting out of the gate. It's probably going to be fastest when they first start out of the gate. So there's really only two kinds of measurements that we're going to do. There's an average rate where we have 2 points on the line, an instantaneous rate where we use a tangent to find those 2 points on the line. And at the very end, we're going to talk about this initial rate, which is a special kind of instantaneous rate. This idea of an initial rate is really important because this is going to be the parameter that we're going to use for our next skill.